To calculate the demand factor for multiple heat pump systems, you can use either NEC section 440.6 or section 220.30. Let's begin with NEC section 440.6. This section provides a table for demand factors based on the number of heat pumps installed. If you have 1 or 2 heat pumps, the demand factor is 100%. For 3 to 6 heat pumps, the demand factor is 75%. For 7 to 12 heat pumps, it's 65%, and for 13 or more heat pumps, the demand factor is 55%. Now let's consider NEC section 220.30C2. This section allows using a demand factor of 100% for the largest heat pump and 50% for each additional heat pump. Here are the steps to use this method. Firstly, determine the largest heat pump load in kVA. Secondly, calculate the total heat pump load in kVA by summing the loads of all the heat pumps. Thirdly, apply the demand factor. Use 100% for the largest heat pump load and 50% for each additional heat pump load. Let's look at an example calculation. Consider a system with 3 heat pumps. Heat pump 1 has a load of 10 kVA, heat pump 2 has a load of 8 kVA, and heat pump 3 has a load of 6 kVA. Using NEC section 440.6, the demand factor for 3 heat pumps is 75%. The total load is 10 kVA plus 8 kVA plus 6 kVA, which equals 24 kVA. The service calculation is 24 kVA multiplied by 75%, resulting in 18 kVA. Now, using NEC section 220.30, the largest heat pump load is 10 kVA. The total heat pump load is still 24 kVA. Applying the demand factor, it's 10 kVA at 100% plus 14 kVA at 50%, which equals 17 kVA. To summarize, both methods can be used to calculate the demand factor for multiple heat pump systems. NEC section 440.6 provides the simplified approach based on the number of heat pumps. NEC section 220.30 allows for more detailed calculations based on the actual heat pump loads. If a significant portion of residences has multiple heat pumps, it might be more efficient to use the NEC section 440.6 table. However, for larger systems or systems with significantly different heat pump loads, NEC section 220.30 may provide a more accurate result. In more detail, let's explore the NEC sections further, explaining how to apply each one effectively and highlighting the advantages and disadvantages of each method. We'll delve into real-world scenarios where each section might be more appropriate, providing a comprehensive understanding of heat pump demand factor calculations. Consider a scenario where you are dealing with a large apartment complex, each unit equipped with multiple heat pumps of varying sizes. In this case, accurately calculating the demand factor is crucial for determining the appropriate service capacity for the entire building. Firstly, let's focus on NEC section 440.6. This section simplifies the calculation by providing a table that correlates the number of heat pumps to a specific demand factor. For example, if there are 5 heat pumps in the entire building, you would apply a 75% demand factor to the total connected load of all heat pumps. The advantage here is its simplicity. It doesn't require detailed information about the individual heat pump sizes. However, the disadvantage is that it may not be as accurate as NEC section 220.30, especially when heat pump sizes vary significantly. Now, let's examine NEC section 220.30C2. This section offers a more granular approach. Firstly, you identify the largest heat pump load. Secondly, treat it at 100%. Thirdly, treat each additional heat pump at 50%. For example, if the largest heat pump is 12 kVA and the other 4 heat pumps are 8 kVA each, you would calculate the demand as follows. 12 kVA at 100% equals 12 kVA. 4 heat pumps at 8 kVA each gives a total of 32 kVA. Applying the 50% demand factor to 32 kVA results in 16 kVA. Add this to the 12 kVA from the largest unit, and the total demand is 28 kVA. This method provides a more precise estimate of the actual load demand, particularly when there's a wide range of heat pump sizes. However, it also requires detailed information on each heat pump's load, making the calculation more involved. In situations where most residences have a similar setup, using NEC section 440.6 can save time and effort. It's especially useful when you need a quick estimate or when the heat pump sizes are relatively uniform. On the other hand, for projects where accuracy is paramount or where heat pump sizes vary greatly, NEC section 220.30 is the preferred method. It provides a more tailored calculation, ensuring the electrical system is appropriately sized to handle the actual load. Keep in mind that local codes and regulations might have specific requirements or amendments to these NEC sections. It's always best to consult with a local authority having jurisdiction to ensure compliance with all applicable codes. Furthermore, when applying these calculations, it's essential to consider other loads in the residence, such as lighting, appliances, and general use receptacles. Heat pump load should be combined with other loads as per the NEC to determine the total service load. Remember to use the appropriate demand factors for these other loads as well, as outlined in the NEC. For example, general lighting and receptacle loads often have demand factors applied based on the square footage of the dwelling. Appliance loads might have specific demand factors as well, depending on the number and type of appliances. When combining all these loads, you arrive at the total calculated load for the residence. This figure is used to determine the size of the service conductors, overcurrent protection, and other electrical components. Additionally, it's a good practice to review the heat pump manufacturer's specifications to verify the load information. The nameplate rating of the heat pump provides the maximum current draw, which is a critical factor in these calculations. Using accurate and up-to-date information ensures the electrical system is designed to handle the expected load safely and efficiently. Furthermore, consider the impact of energy-efficient heat pumps and other energy-saving measures. Energy-efficient models often have low power consumption, which can affect the demand factor calculation. However, it's essential not to underestimate the load, as heat pumps can draw significant current during startup and peak operation. Designing the electrical system with sufficient capacity ensures reliable performance and prevents potential overloads. In summary, calculating the demand factor for multiple heat pump systems involves considering both the number of heat pumps and their individual loads. NEC section 440.6 offers a simplified approach, while NEC section 220.30 provides a more detailed calculation. Selecting the appropriate method depends on the specific project requirements, the uniformity of heat pump sizes, and the level of accuracy desired. Always consult the latest edition of the NEC and local codes to ensure compliance and safe electrical practices. When you are dealing with a situation involving multiple heat pumps in a single residence, further considerations come into play, especially regarding the diversity of operation and potential for load shedding. Diversity, in this context, refers to the likelihood that not all heat pumps will operate at their maximum load simultaneously. This is particularly relevant in residential settings, where occupants may adjust thermostats in different rooms or at different times, leading to variations in heat pump usage. To account for diversity, you can refine your demand factor calculations by considering the typical usage patterns and occupancy schedules of the residence. For instance, if the residence is occupied by a single individual who primarily uses 1 or 2 rooms, the actual load demand may be significantly lower than the calculated demand based on all heat pumps operating at full capacity. In such cases, you might justify a lower demand factor than what is prescribed in NEC section 440.6 or 220.30. However, this requires careful assessment and documentation to support the reduced demand factor. Load shedding is another strategy that can be employed to manage the demand on the electrical system. Load shedding involves selectively disconnecting or reducing the load of certain appliances or equipment during peak demand periods. This can be achieved through various means, such as smart thermostats, energy management systems, or manual controls. By implementing load shedding for heat pumps, you can limit the maximum demand on the electrical system, allowing for smaller service capacity and reduced infrastructure costs. For example, if the residence has multiple heat pumps, you could program the system to prioritize certain units over others during peak demand periods. This would ensure that essential areas, such as living rooms and bedrooms, maintain comfortable temperatures while temporarily reducing or disconnecting heat pumps in less critical areas. Load shedding can be particularly effective in residences with multiple heat pumps, as it allows for flexible control over energy consumption and demand. However, it's crucial to design the system carefully to avoid compromising comfort or safety. The load shedding strategy should be transparent to the occupants, and they should have the ability to override the system if necessary. Furthermore, the system should be designed to prevent overloading the electrical system, even if all heat pumps are allowed to operate simultaneously. In addition to diversity and load shedding, it's essential to consider the impact of energy storage systems such as batteries on the demand factor calculation. Energy storage systems can store excess energy during off-peak periods and discharge it during peak demand periods, reducing the reliance on the grid and lowering the overall demand on the electrical system. By integrating energy storage with heat pump systems, you can further optimize energy consumption and reduce demand charges. For example, the energy storage system could be used to power the heat pumps during peak demand periods, effectively shifting the load away from the grid. This can significantly reduce the calculated demand for the residents, allowing for a smaller service capacity and lower electricity bills. However, the integration of energy storage systems requires careful planning and coordination with the electrical system. The energy storage system must be properly sized to meet the load requirements of the heat pumps, and the system must be designed to ensure safe and reliable operation. Furthermore, the energy storage system must comply with all applicable codes and regulations. In summary, when calculating the demand factor for multiple heat pump systems, it's essential to consider the diversity of operation, potential for load shedding, and the impact of energy storage systems. By incorporating these factors into the calculation, you can optimize energy consumption, reduce demand charges, and ensure the electrical system is appropriately sized to meet the actual load requirements of the residents. Always consult with qualified professionals and adhere to applicable codes and regulations to ensure safe and reliable operation.